This is going to be a pretty short video that outlines a very important concept you have to come to terms with. This is a concept of using your balanced chemical equation to come up with a factor that allows you to convert between moles of one substance and moles of another substance. So these factors, as you'll see in a minute, I call equation factors, and it's really quite straightforward because we've already dealt with conversion factors, and so an equation factor is simply a conversion factor we get from a balanced chemical equation. So let's get stuck into it. So here we have a chemical equation, and so this equation is not balanced. So we're going to go ahead and balance this equation. So I look at the carbons. I have 2 carbons here, CO2, so I balance with 2 carbons. I have water, H2O. I'm going to balance the hydrogens by balancing with water, and I have 6 hydrogens in my reactant, so 3 water molecules. And now I'm going to balance the oxygens. I have 7. I have 1 plus 6 makes 7. So there's the balanced chemical equation. Now the important thing here is the question is, what are these equation factors telling, or what are these coefficients telling us? Well, if you think of this at the molecular level, it's pretty straightforward. 1 molecule of ethanol reacts with 3 molecules of water. So if I happen to have 3 molecules of water around and 1 molecule of ethanol, a reaction would proceed, and I would produce my products. Hypothetically, if I only had 2 molecules of water there, I wouldn't get a reaction. I require at least 3 molecules. So at the atomic level, it's looking at how molecules interact. But as I've said before, we don't very often deal at the atomic level. We deal at the level of the mole, which is a measurable amount of chemical compounds. Remember, 1 mole, 6.02 times 10 to the 23rd particles. So when we have a mole of substance, we have a lot of them. And so if we look at this at the level of mole, this is really what we're looking at as being important. What these coefficients are then telling us is 1 mole of ethanol reacts with 3 moles of oxygen. So these coefficients are molar ratios. This is very important. These are the ratios by which reactants interact with one another. 1 mole of methanol reacts with 3 moles of oxygen. These ratios are also telling something about the products, though. If I react 3 moles of oxygen, I would produce 2 moles of carbon dioxide. If I react 1 mole of ethanol, I could produce 3 moles of water. So these mole ratios are what we're going to use. So we get those from our equation. So as I said, I call these equation factors, and you're familiar with equation or conversion factors. We've already looked at conversion factors like the molar mass. If you remember the molar mass, it's simply a ratio of a certain number of grams to moles. And we see that represented as, for example, with hydrogen, as 1.01 gram per 1 mole. Or we could list that as 1 mole per 1.01 grams. So it's just a ratio, and the molar mass, and that ratio then we can express one of 2 ways as a conversion factor. Well, the Avogadro constant we've also seen as a ratio of entities per 2 mole. And again, we have that 6.02 times 10 to the 23rd. Chemical entities, for example, atoms, per 1 mole. Or we could express it the other way as mole per Avogadro's constant of atoms. And so you've seen these conversion factors. You're familiar with these conversion factors. Well, an equation factor is simply that ratio between the number of moles of different chemicals used or produced in a chemical reaction, and the important bit here is the equation factor is obtained from a balanced chemical equation. You have to remember that. That's why you always have to check that your equation is balanced. So remember that. All right. Let's carry on. So first of all, we're going to balance this equation. So this is the equation for the synthesis of ammonia gas. And if I balance this, I look at the hydrogens, 2 hydrogens, 3, I know I'm going to have to even that up, so I make that 2 ammonia, I make that 3 hydrogens, and lo and behold, it's now balanced. So now, equation factor, because then these are the ratios. Well, let's just look at this nitrogen to hydrogen ratio first. I can write that as a ratio as 1 to 3. I could also add a 2 for the ammonia. So there's all of my ratios. And so I get equation factors from those ratios. So let's deal with nitrogen and hydrogen first. So as an equation factor, I could have 1 mole of nitrogen per 3 moles of hydrogen. Or I could have the opposite, which is 3 moles of hydrogen per 1 mole of nitrogen. So that's one ratio. Well, I can also have a ratio between hydrogen or nitrogen and ammonia. 1 mole of nitrogen per 2 moles of ammonia. That's what the coefficient is telling me. Or 2 moles of ammonia per 1 mole of nitrogen. And finally, I can have the ratio of hydrogen to nitrogen, and so that's going to be 3 moles of hydrogen, H2, per 2 moles of ammonia, or 2 moles of ammonia to 3 moles of hydrogen. So in that one chemical equation with those different coefficients, I've managed to generate 6 different equation factors. And we use the equation factor to do mole conversion. So whatever I'm looking for, I'm going to come up with the appropriate equation factor. So let's have a look at that now. So this is then a conversion from moles to moles. So equation factors are used to move from moles of one substance to moles of another substance within the reaction. This is really what you have to get out of this. These coefficients allow us to convert between moles of one and moles of another. It's a very common step. You really need to get a grip on this one. So let's have a look at this example. So there's an equation. Again, the synthesis of carbon monoxide from carbon and oxygen. 2 moles of carbon solid plus 1 mole of oxygen gas yield 2 moles of CO, carbon monoxide gas. And you'll see it's balanced as written. So if 2 moles of carbon is reacted with lots of oxygen, we just know oxygen is not going to run out. So we have 2 moles of carbon. How many moles of carbon monoxide are produced? So we're looking for an amount of carbon monoxide. So number of moles carbon monoxide equals, well, we start with 2.0 moles of carbon. And we're going to multiply by an equation factor. Now that factor, like we've always dealt with factors, is going to be a fraction. I want to get rid of my moles of carbon. So I'm going to put moles of carbon on the bottom, and I want to be left with moles of carbon monoxide. So there it is on the top. So you see moles of carbon are going to divide out. Now I just put in the appropriate coefficient. So 2 moles of carbon, so that's going to go on the bottom, and 2 moles of carbon monoxide. So that's going to go on the top. Now if you look at the unit analysis, moles of carbon divide out. Well, 2 divided by 2 is also 1. I'm left with moles of carbon monoxide. So I have 2.0 moles carbon monoxide. Now, this is pretty easy because it's a 2 to 2 ratio, which is the same as a 1 to 1 ratio. So there's no way you can write this. Because it's so simple, you can just write down the actual molar amount. 2 divided by 2 is 1, 1 to 1 ratio. If I start with 2 moles of carbon, I'm going to produce 2 moles of carbon monoxide. And then to clarify that you know what you're doing, I just want you to write right next to it in brackets 1 to 1 ratio. So instead of going through this long process for a 1 to 1 ratio, you can simply write down the molar amount. If you want to do this for a 1 to 1 ratio, by all means, but you don't have to. So let's look at another example. Same equation, 2 moles of carbon plus 1 mole of oxygen yield carbon monoxide. Now, if 2 moles of oxygen is reacted with lots of carbon, how many moles of carbon monoxide are produced? So now we're looking at oxygen. Okay? So number of moles of carbon monoxide, still what we're looking for, equals number of moles of oxygen, which is 2.0 moles, of O2, and I just multiply it by the appropriate equation factor. I want to get rid of oxygen, so it's on the bottom, and my coefficient for oxygen is 1. I want to be left with carbon monoxide, and it's 2 moles of carbon monoxide. And again, unit analysis, moles of oxygen divide out. I no longer have moles of oxygen, I have moles of carbon monoxide, so I know by unit analysis I should be right, and then I do the multiplication. And I get 4 moles carbon monoxide. So that's all there is to it. So in this first sample question, we've shown that the different reactants are going to, same number of moles of both of those reactants yielded a different amount of product. So this is why you have to look at the mole to mole conversion. Let's do one more sample. Okay, so here we go. So 2.72 moles of sodium cyanide is utilized in a reaction. How many moles of hydrogen peroxide are produced? This is hydrogen peroxide. So for that first example, what are we looking for? Number of moles, H2O2, equals 0.272 moles sodium cyanide. This is sodium cyanide, NaCN. And we're going to multiply that by an equation factor. And the equation factor, again, we want to be left with hydrogen peroxide, and we have 1 mole of it. So 1 mole H2O2 divided by 4 moles of sodium cyanide, NaCN. And again, moles of sodium cyanide divide out, and we're left with our 0.272 moles divided by 4, and that equals 0.0680 moles of hydrogen peroxide. Okay, so the correct equation factor gives us the correct number of moles. Second one, how many moles of sodium hydroxide are produced? Now we're looking for number of moles of sodium hydroxide. And so that's going to be a different equation factor, 0.272 moles sodium cyanide. And again, we still know how much sodium cyanide we have, and we're going to multiply by an equation factor, and we want to be left with moles of sodium hydroxide. So 2 moles NaOH from our equation divided by 4 moles of sodium cyanide, NaCN. And so that equals, again, mole of sodium cyanide divided out, and so 0.272 divided by 2 is 0.136 moles of sodium hydroxide. But there actually is another way you can do this. Notice we actually have here, we've calculated a molar amount of hydrogen peroxide. Now, because we have a balanced equation and because we now know a molar amount of hydrogen peroxide, we can use this to calculate an amount of sodium hydroxide. So why don't we try that? So what we're looking at here is number of moles of sodium hydroxide equals the number of moles of hydrogen peroxide we calculated, which was 0.068 moles of hydrogen peroxide. And we're going to multiply by an appropriate equation factor. Let's just quickly go back to our equation. So now we're trying to get rid of hydrogen peroxide, H2O2, which just has a mole ratio of 1. And we're trying to find sodium hydroxide, which has 2 moles, a coefficient of 2. So it's going to be, as an equation factor, 2 moles of NaOH divided by 1 mole of hydrogen peroxide, H2O2. Hydrogen peroxide divides out, so it's 0.068 to multiply by 2, which equals 0.136 moles of NaOH, which, if we check with our previous answer, is the same, 0.136 moles of NaOH using a molar amount of sodium cyanide, 0.136 moles of sodium hydroxide using a molar amount of hydrogen peroxide. So it doesn't really matter which way you come at it. If you know the molar amount of a substance, you can find the molar amount of any other substance using balanced chemical equations, those molar ratios, and equation factors. And that concludes this video.